have cooling a plate in different orientations. So we have ABC, a vertical plate, a plate facing up, and a plate facing downwards. And we want to figure out the rate of heat transfer. We know that the rate of heat transfer changes depending on how the hot face of a plate is facing. So let's grab our table, which will be very important for this question. So the first question is vertical plate. We can just start with the Rayleigh number. That's fine. We don't have to look at the table for that. So the Rayleigh number is G times beta times Ts minus T infinity all over the square of kinematic viscosity times L cubed times the Prandtl number. And beta, what do we have? It's in a room, so we can assume air. Air is an ideal gas, so we know that beta is just 1 over the film temperature, and make sure that's in Kelvin, 133 degrees. So now we can start substituting in values. This is the metric system, so 9.81. We just said beta was 1 over 333 times Ts minus T infinity. Let's see. Okay, so that's the room temperature is 90 degrees. And the plate temperature is 30 degrees. We want the absolute value basically. So 90 minus 30 times L cubed. Oh, the room is 30 degrees Celsius. That makes more sense. And then L cubed, what is L? Okay, so it's a 0.6 by 0.6. So it would make sense that L is 0.6. So 0.6 cubed. Kinematic viscosity is given to us 1.896 times 10 to the negative 5 squared times the Prandtl number. Is that given to us? It is 0.7202. So we type all of this into our calculator and we get 7.649 times 10 to the 8. Perfect. So now we have that, and we can calculate the Newson number for part A. The Newson number for a vertical plate. So what is the Rayleigh number? 10 to the 8. So we could use this 10 to the 9 equation. So I think I'm going to check both of these just for fun. So the Newson number is 0.59 times the Rayleigh number to the 1/4. So here I got about 99. Or we can use this other equation here. So the Newson number is 0.825 plus 0.387 times the Rayleigh number to the 1/6. over 1 plus 0.492 times the Prandtl number, 9/16, and then all of this to the 8/27, and then this entire thing is squared. And this Nusselt number is 113.3. So this one is more accurate. And so we'll use this to calculate our H. But it's fun to just see how the numbers compare. So H is KL times the Nusselt number. So L.6, the Nusselt number is 113.3. And K was given 0.02808. So this gives us 5.302 watts per meter squared Kelvin. Perfect. And we know that the area is just 0.6 squared. That's the area of a square. And so we can find Q dot with HAS TS minus T infinity so that is the H we just calculated, 0.36 times the difference in temperature is equal to 115 watts. So this is for the vertical plate. And then we have to figure out what LC is for the hot plate. So we have where the hot surface is either up or down. So the characteristic length, instead of it being L, is actually AS over P. So the Rayleigh number does change. So L is actually AS over P. So we know that the surface area is 0.6 squared. We just calculated that before. Times the perimeter is 4 times 0.6. A 0.6 cancels out. So 0.6 over 4, or 0.15 meters. So using this as our L, we can calculate this Rayleigh number. GB, or beta, TS minus T infinity, LC cubed, times the Prandtl number, times the kinematic viscosity. 9.81. One over 333. 90 minus 30. 0.15 cubed. And then the Prandtl number was 0.7202. And then kinematic viscosity was 1.896 times 10 to the negative 5 squared. We get all of this. The Rayleigh number is 1.195 times 10 to the 7th. Great. So now for the hot plate facing up, that's this one. So we have these for the Nusselt number, and we'll just have, we need to see 10 to the 7th. So it's on the border between the two. So it doesn't matter too much. I'm going to go with, which one do I want to go with? I'll go with the first one because it's the first one. So the Nusselt number, again, because it's on the border, it doesn't really matter which one you use. You'll get a different answer, but it should be as equally as correct. So the Nusselt number, 0.59 to the 4th. Okay. 0.59 times 1.195 times 10 to the 7th to the 1/4 is 31.75. Then we have H is KLC times the Nusselt number, and we have all of those. So we'll just calculate the H is 5.944. And we have Q dot is HAS TS minus T infinity, everyone's favorite equation, 5.944.36. This time we do use the full area. It is the surface area, not the characteristic length. So don't get used to using the characteristic length and then use that instead of surface area. So we have 90 minus 30. So this Q dot is 128 watts. And then the last one, part C, the hot face is now at the bottom. So that's part B of that other table here. We can use the same characteristic length, which means that the Rayleigh number does not change. We don't have to calculate that again. But the Nusselt number does change. And our Rayleigh number is between 10 to the 5 and 10 to the 11th. So we're good there. And we can use this formula, 0.27 times Rayleigh to the 1/4. So the Nusselt number is 0.27 Rayleigh to the 1/4. We get 15.87 if we substitute in the Rayleigh number from before. So H is KLC times the Nusselt number. Plug in this Nusselt number, plug in the stuff from before. Same LC. Actually, I'll write it out for you because I can. So same K, the LC is 0.15 because of this Rayleigh number. 15.87. We get the H is 2.971 watts per meter squared Kelvin. And then we get that Q dot the only thing that changes in this equation is H. A stays the same, TS stays the same, T infinity stays the same. 64.2 watts. So the power drastically changes depending on the orientation of the plate. Not a particularly difficult question, it's just a very time-consuming one.